Here's your clicker.
Well, we get to come back. Wow, thank you. The beginning and the end. I feel like people were probably maybe more awake in the beginning, so I'll try to bring some exciting energy to the end of today's discussion. Thank you, Murray. Kate Avery from Deloitte. I told my mom that I was speaking at this conference in Miami, and she was like, well, what's it about? And I said, well, it's about quantum computing. And she said, do you know how to turn your computer on? I'm like, well, on a good day, yes. But in all seriousness, I am not, probably like the majority of you, quantum physicists or quantum experts or even someone who knows how to add well. Instead, I am someone who spends a lot of my time working with clients on complicated problems that I just want to solve better for them. And the reason that I still get up every day and am excited about quantum computing and what D-Wave can help to do is because I see the ability to help our clients do things faster and more accurately when it matters. And so I'm really excited to be joined by my friend and colleague, Scott Buckles. He is all things quantum. Every Friday morning, he and I chat, and he teaches me just a little bit more about quantum computing. So Scott, over to you.
Thanks, Kate. So Scott Buckles, as everybody's mentioned, I have the privilege of leading our quantum computing efforts at Deloitte. I thought I might share a couple things first. So what I've found over the years is, even more so when I go to some of these conferences, is not everybody is familiar with Deloitte. Deloitte is the world's largest professional services firm. We employ over 400,000 people in just about every country in the world, and we do an enormous amount of technology implementation support. And so we spend a lot of time with a lot of really smart people and really large customers solving complex technology problems. The next question I sometimes get is, why is Deloitte doing anything with quantum computing? The answer to that is a lot of our customers, and even for ourselves, we want to know what's next in terms of technology, what's over the horizon, what is emerging, what's important, and how do we make sure that we are helping people understand what they're reading in the news, what's actually possible, and sort of distilling the art of bringing the future forward. So then the third thing I would tell you about is I've spent the last number of years working in our emerging technology group, among other things, and there part of what we're trying to do is help bring the future forward for our large customers. And we've found that when we're trying to bring the future forward, when we're trying to bring emerging technologies out of the lab and into the real world, that three things tend to be really helpful. So the first thing is stories. And you've spent the day listening to stories and use cases from people about how quantum computers can be used. Those are really important when we're trying to help people understand and visualize how this might be useful for you. The second thing that we've found is really important are proofs of concept. And if you'd like to learn more about how we do proofs of concept and prototypes, find Kate or I afterwards, and we're happy to tell you all about it. The last thing that we've found is helpful, or that I've found is helpful, is we think about emerging technologies as mental models. And what I'm going to do is share with you one mental model I find useful as I go around and talk to people all over the world about quantum computing. This is probably not as important for this audience, and yet I suspect many of you may find yourselves trying to explain to a colleague, to your grandmother, or somebody else at a cocktail party how a quantum computer works and how it's different. So here's my offer to you, which is I sometimes find some of the best analogy for people is the idea of soap bubbles. So many of you know classical computers are really at their heart math machines. So everything that's up here on the screen, all of the simulations, all of the video, all of the everything is just a lot of math turning really fast. And sometimes when we say quantum computers are like supercomputers, people go intuitively, oh, so I can do more math even faster. And what we have to tell people is, think about when you blow a soap bubble. If I needed to know what shape that bubble was going to take when a child is blowing through the little soap wand, I can do a lot of math. And I can spend a lot of time doing a lot of math really fast, and in a couple of weeks, I can tell you That is going to make a sphere every single time. And yet when you blow a soap bubble, it almost instantaneously becomes a sphere. So one of two things must be true. Either soap film is a mathematical genius beyond anything that we've ever seen in the world, or it just works differently. And sometimes what's important for us to remember is new stuff sometimes works differently than the things we already have. Quantum computers, as all of you understand, are more like that soap film and less like a giant calculating device. And the challenge, of course, is therefore, how do you turn a problem into something that can be solved through soap film, right? How do we map our questions onto physics as opposed to mapping them onto math? Because we've spent 60 years or more getting really good at mapping problems onto math. So that I leave you to start with. And now what we're going to do is we're going to switch gears a little bit. And we're going to talk a little bit about some of the use cases, some of the things our researchers are finding. And then we're happy to take any questions, although Kate and I are also keenly aware that we're standing between everybody and drinks. So we're endeavoring to be concise. So with that, Kate.
Thanks, Scott.
Actually.
So one of the things that I'm most excited about that we're working with clients on right now actually has to do with space. Now, I'm sure, again, if the Wall Street Journal was still up here from Alan's opening this morning, we could flip through it and easily see that SpaceX or others are launching rockets. They're trying to build their own launch pads. But many folks don't know that the vast majority of rocket launches that occur on government infrastructure. And as a result of that, there is increasing demand for finite resources. So our clients within the Space Force and Air Force are worried about this and are thinking a lot of time. And they have come to us to help them just noodle through the concept of how could they potentially optimize launches. I won't go into anything that's confidential, but think about this. Just like the scheduling variables that you heard about this morning when it came to the airport security, there are many different companies that are competing for a finite amount of time that have all sorts of delays that are related to weather, that are related to technical changes, that are related to, frankly, financial impacts that are occurring in the economy that are funding or not funding launches. So when we think about space, and I wish that I had brought my space helmet or something so that I could rival Alan's great costume changes earlier in the day, we are thinking about how we might be able to apply D-Wave's quantum annealing compute to solving this challenge. The other thing that we do a little bit differently at Deloitte, which I don't think has been touched upon too much today, is really about making this very useful. So if you think about the commercial enterprises that want to be able to schedule their rocket launch, they are not going to be scientists. They are going to want a simple interface, quite like the way that we use Uber today. So we are going to, again, partner and think about human-centered design and how we can put something very accessible on the front of something that behind the scenes is extraordinarily complex. And hopefully help our government clients to think about how they can better optimize launches so that as demand increases, it doesn't slow down the number of rockets that are going into space to do all sorts of useful things for us, but actually can do it much more efficiently and accurately. So with that, Scott, over to you for the next one.
Sure. I think, as many of you understand, when we're looking at quantum annealers, we've discovered that there are a number of problems that map well onto optimization. A lot of those, as was indicated by one of the talks this morning, are things that we can map onto various sort of traveling salesmen and other well-known computer science problems where the solution is difficult to calculate classically, and it turns out to be possible to simulate or to be able to use an annealer to solve in far quicker with higher accuracy. And so it turns out that when we're looking around for problems, things that are very complex, that have lots of moving parts and variables, like space, tend to be really interesting problems. So one of those interesting problems is also this idea of optimizing clinical trials. So unless many of you are in the pharmaceutical industry, it may be difficult to appreciate how difficult it is becoming these days to schedule a drug trial. It turns out that drugs are increasingly specialized. If you're a drug company, it costs you hundreds of millions or billions of dollars to identify drugs. You then are trying to identify a very specific set of people. You need those people to be in places that have the capability to deliver them the medication that you're actually providing, or increasingly the capability to actually do the genetic engineering manipulation that's required for some of the advanced technologies. You need patients who are in certain circumstances, because you need people sick enough to be cured, but not so sick that they're likely to pass away. It has to work in a certain period of time. The complexity is actually staggering, and the problem is becoming increasingly difficult as time goes on because of the specialization of these drugs. And so one of the things that we have been actively investigating is figuring out, as the pharmaceutical companies are collecting larger volumes of information and have increased capabilities in terms of knowledge of all of the things that need to be decided, helping them figure out, how do I optimize where I'm going to do my drug trials? Whom am I going to admit to the trials? Which hospitals will we be working with to perform the trials, and so forth? It turns out that this is an incredibly important question, because this is the gateway to get us from the discoveries that exist in the lab into the real world. And so this winds up being one of those really interesting high-order complexity problems that tends to lend itself well to annealers. Another example of problems that I think people will find interesting, and I will tell you these are some of our very recent results, is we've been thinking about how we use quantum annealers to solve fraud detection. So if you think about the volume of credit card transactions, it becomes very complex, right? And we have a long history of using classical techniques to try to identify fraud in institutions. Those techniques are extremely effective, right? The first thing that we all have to recognize is that nobody in their right mind wants to displace the way we do work today across the board. What we're trying to do, though, is figure out, are there places where we can do narrow but very effective optimization of the things that run in production today? So how do we tweak what's there to make it better? There are at least two different places where we've found that this actually makes a big difference. One is something that's been mentioned along the way today. It's the idea of feature selection. So for those who are not data scientists, if you think about your credit card company, they probably know both your credit score and your proclivity to pay your bill. And it turns out that those two things are probably fairly highly correlated, but one of them might be a better piece of information. And so what feature selection is trying to do is take the hundreds of thousands of things that are known about you and figure out, for this problem, what are the ones that are most MECE, mutually exclusive and collectively exhaustive. And it turns out that quantum annealers are actually particularly good at identifying high-quality features, more so in a number of cases than some of our best classical techniques, in addition to working faster. So that becomes one piece of our data science pipeline that we can look at. Another thing that we've discovered about quantum annealing is that it is particularly good at creating what we call ensemble models. And ensemble models is essentially a collection of naive models that, when combined together, produce a result that is equivalent to or better than our best deep neural network learning models. That's important because you can actually explain an ensemble model to a mere human, whereas trying to understand what's going on under the covers in a deep neural network is exceedingly difficult. And so it turns out that what we've actually been doing is playing around with some fraud data. We've been using light GBM, which, for those who don't know, is one of the best classical techniques for actually doing machine learning and predictive modeling. And we are finding that we can generally produce comparable or better results with sort of easier inferencing and sort of equivalent quality that are basically by using the two quantum techniques that I was talking about. So feature selection on the annealing side, and then building of ensemble models. This turns out to be really exciting for a number of reasons. It is potentially a new option for large financial services firms to look at. Our results have demonstrated in some cases we get better results for fraud detection than light GBM, which is a fiendishly difficult thing to beat. And so we're really excited about that result and are happy to talk about it. In fact, the researchers who did the work are here with us, and they're more than happy to answer any questions you have at the break. So in short, a lot of what we wanted to tell you is just the good news is that quantum annealing and sort of by extension some of the other quantum-related technologies are increasingly making their way out of the lab and out of research into production. As Kate mentioned, and in fact as was described in the Port Authority example earlier, they don't always have to show up in a way that looks like something only a PhD can love. They can be doing work behind the scenes, just sending you a message in your app, and when you combine the knowledge of how to actually do those things with the knowledge of how to design systems for humans, and you also add in some of my favorite, which is social engineering, which is actually getting people to do the things you want them to, when you put that stuff together, magic happens. Because what winds up happening is you have technology that is emerging, that's easy to use, and that people actually want to use. And so with that, thank you for your time, and it was a pleasure talking with all of you.
Okay, if I ask you a question before we conclude? Thanks, everyone. So Scott and Kate, we've been on a number of calls with customers and clients and things, and I wanted to ask you, what are your comments or observations about the relative proportion of, let's say, folks in government or in enterprise who are kind of pursuing quantum computing from the technology side versus from the solution side? So Bob talked about there's a number of folks who are largely just, I'm looking for a solution and something that will solve my problem. And there are also folks who are looking for, getting into advanced technology and making sure their organizations are ready. What are you observing in those customer conversations?
Scott, I'll try to take it if that's okay.
Sure.
So I have been on a journey myself as I've kind of discussed with clients their challenges and problems. I am oriented to being a problem or a solution provider versus a technologist. What I have found is the minute that you say the word quantum, the dynamic of the conversation changes. Because quantum to many business-minded individuals, is something that they don't understand and therefore are a little bit afraid of. So over the course of the past 18 months, as I have gotten the chance to talk more about quantum and think more about quantum solutions, I very much position it with our clients as something that if you need the right answer and you need it fast, we have a way to potentially solve it for you. And so that's really the way that I am tackling it. And I found that that seems to resonate more with our clients, because the moment that I have said quantum, I get, generally speaking, quizzical questions, intellectual questions, but not the desire to apply it practically. We often get shunted over to a research and development department, or the one or two token quantum physicists that exist within an organization. So my advice is lead with solutions.
Mm-hmm. Lead with solutions. That's a fantastic answer. And Scott, thoughts or comments from your perspective?
I would say, in addition to everything Kate said, what we see is when there are a group of people who really want to do something cool, and therefore show up asking the question, I really want to do something cool, I have a hammer, in this case quantum annealing, what problem can I solve with it? We have another group of people who show up saying, I have a problem, I just want it solved. I don't care if the answer is pen and paper, just give me the best solution. I don't think those are mutually exclusive. because what winds up happening is you get to similar answers just through different mechanisms, but they wind up being very different conversations. On one hand, it is a journey of discovery. Let's go look for the kinds of problems that the tool that you want to use is well suited for. On the other hand, it is a bit of a, well, that's an interesting problem. It seems like you've thought through really hard what the problem is. Can I ask you a few questions to make sure that I understand and you actually properly understand the nature of your problem so that we can help you with the solution?
And in terms of when you're talking with customers and you are able to make relations to some of the kinds of applications that were discussed today, does that help those customers to kind of be like, oh, okay, like if there are other examples that they can see in comparable use cases, does that build the bridge for them, particularly to maybe sidestep the quantum complexity aspect of it to kind of express an interest? Kate, what are your thoughts there?
Yeah, oh no, it definitely does. I think that that's actually one of the most powerful things that we can do is to show and talk about examples. I mean, Murray, you and I have had probably, I don't know, a dozen conversations on this topic and with others. But I think one thing that does often happen is there's a trust factor that they see the demos, they see the examples, but then they want to understand before they actually go and do. So it's kind of it's an evolutionary discussion with them, but more examples, the better.
Yeah, yeah. And Scott, in terms of the team that you work with, right? Yep. So they're focusing on understanding the broader quantum industry in order to help customers kind of understand the space and what's happening in the industry, but also learning the skills to apply it and program it. What would you say has been their experience in terms of like coming up to speed with the tech and their process?
Bringing people up to speed on new technology is always an adventure. What I would loosely say is, the nice thing about quantum annealing is that when we bring in people with strong math backgrounds and when we bring in people with data science backgrounds, they often find the transition more straightforward. Okay. When we bring sometimes in some of our computer science folks who don't have as strong math backgrounds, we have had different experiences. And so I think a lot of it is just thinking about, for this technology, what's the right skill set that you need on the underlying level, and what's the right attitude that you actually need in the person. We have people annealing at least as straightforward. When we get into some of the gate technologies, they can actually take 2 years for people to get their heads wrapped around, and people generally want to go really fast, really quickly. And that's actually when we point them more at annealing, because it is a more easy to use, less head-bendy kind of thing to deal with, which is a great advantage, particularly when you're trying to get something done quickly.
Terrific. Well, thank you both for sharing your experiences today. Let's give Scott and Kate another round of applause and thank them for coming up. Thank you both.